You cannot stand up for the duration if you sit there, Luke. You're right in front of the camera. Luke, move the over there.
10, 9, 8, 6, 5, 4, 3. Hey guys, silence on the set.
Hello, everybody. Welcome to the 2022 Bar Z Bash. We're doing the live TIG demonstration. And I want to welcome everybody here. We're going to do a couple little announcements here real quick while we give people time to get signed on. The first announcement is down in the description. If you haven't already, there is a link that you can click on that it will take you to the classroom material we're going to be talking about today, and it is in a PDF format and in a PowerPoint format, so if you want to watch it on a laptop. Also, we're going to put a QR code up. You click on that QR code. If you're a QR code person, that will take you to either the PDF version for printable or the PowerPoint if you want to follow along on your computer. You want to split screen it and follow it along. So while everybody's taking a few minutes to get on here and print that out and get followed along, I want to do a couple of housekeeping things here, okay? First of all, I want to give a big thanks to all of my friends at Lincoln Electric. Lincoln Electric made this possible this year. Lots of support here for the Bar Z Bash, for everything that we're trying to do to educate the young folks, pass on what all of us older guys already know to that younger generation. Now, speaking of younger generations, I'd like to bring my younger generations up here. Come on, guys. Come back here. And the queen bee. That's you too, honey. And I want to tell everybody why. Are they in frame? They in? Everybody in? Come on in. Scoot in. I want to tell everybody, this is the reason that I'm here. You can thank her. The other reason I'll tell you about in a minute, but she is the one that makes it possible. These are my boys. I bring them along. They help out Stan. They all got straight A's in school this year because otherwise they wouldn't be here. That's the standard I set, and Dad had to pay that airplane ticket. Thank you very much for that high cost. But it was tickets, yeah, but it was worth it. Little special honor this guy got. He got the highest math and the highest reading score in the entire school this year, so we're pretty proud of him. And my beautiful wife, Michelle, she makes it all possible by putting up with all of the crazy hours of filming and going here and going there and dragging her all the way across the country for all of this. All right, guys, have a seat. And while everyone's a little bit more housekeeping, we want to take a huge thanks out to Stan Zankowski. Stan, come up here, Stan. For those at home that have never been to the Bar Z Bash, you have no idea how much this man does behind the scenes in his own yard. We're in his backyard right now to make this possible.
Well, by the way, there's a QR code down in the bottom here. It's over on this side. Point over there. The QR code's over there. I just saw it on my screen. Are we pointing to the QR code? We're doing good. All right, go there. That's the curriculum for what Jim's about to teach.
That's all of this. You can print it or watch it on your laptop.
Everything the audience has, you're going to have. So go down, hit the QR code, go down to the description. That is a link to my personal Dropbox. You can download the curriculum in a PDF or a PowerPoint, whatever your preference.
I already said that.
I said it again.
Huh.
You don't talk about enough. You got a good-looking family. Will you adopt me? I don't take up much room, and I don't eat much.
Stan, you would break the mold, though.
I have
a good-looking family.
Oh. I'm going to go back to my comments. You guys that are watching on the internet, if you got a comment or a question for Jim, go ahead and throw it in the comments. I'm going to be sitting there watching. I'll ask him. He can answer you, maybe not in real time, but he'll answer your questions. And enjoy the class. And thank you for doing this, bud.
You are very welcome. So again, like Stan said, if you are on if you are on the live feed and you have a comment, enable chats. You can type in your question. Stan will raise his hand. I'll answer it, and I'll try to answer your question. Now, a couple other things. Thanks to our friends at Lincoln Electric, who again made this possible for supporting this endeavor. year after year, and especially this year, they've helped out huge. They've made a discount coupon for everybody that's here at the bash that wants to buy equipment or gear. So yeah, it's an advertisement, but at the same time, a lot of folks, this enables them to buy equipment where they can't normally afford equipment on their own. This is for just watchers and attendees of the Barzy Bash, okay? It's $400 off the TIG 200. We're talking about the TIG 200 a lot today because this is the machine that most directly applies to most of us at home. All right, $400 off, so it'll put this machine a little bit under 2,000 bucks. Okay, the Bash 400. We're gonna put a copy of the card up there on the screen for you guys so you can see it. Also, any other equipment is 10% off. That's Barzy Bash 10, and gear like helmets, hoods, glasses, jackets. All of the kind of gear, chipping hammers, that kind of stuff, is 20% off, okay? And that goes on until the beginning of August. So you got a good amount of time to go out and buy the equipment if you want at home. Now, for those of you that are in attendance, there's a red folder that's out. This folder right here, everybody see it? Inside that folder will be this handout. If there's not, please raise your hand and we'll get you one. Those that are in attendance, you guys have a copy of the card in there. Did anybody not get a handout? Anybody got one that wanted one? For those who do not know who I am, my name is Jim Bollinger. I am a YouTuber. Name of my channel is Do Right Fabrication. For those in attendance, I printed this out with my own QR code that'll take you to my channel. We do lots of fun stuff. It's not just welding, it's fabrication. It's all kinds of neat and interesting things that I think are neat and interesting. My full-time profession that feeds that family of mine that you saw is not a welder. I am an engineer paramedic for the Orlando Fire Department. So it's a little bit different from what you're normally used to seeing up here. My passion and my start in this got started when I was a little kid, and I started welding at a very young age. For those of you that are in attendance, you see there's some copies of the ARC magazine floating around. You can hear the whole story. It's all in the ARC magazine. And with that being said, is there any problem, Stan, with people getting the information so we can go ahead and get started? Everything looks like it's hot to trot. I like it. Okay, so.
What didn't happen is when you held that card up, it was a terrible fade.
Okay. Do I need to
hold the camera later or get a photograph?
Yeah, I can hold that up for everybody on the live feed.
And also, Jim, you can tell them in the chat section, I'm putting up a link to your YouTube page.
Okay, so in the chat section, there'll be a link to my YouTube page. I'd also like to give a quick shout out. If everybody that's in person turns around and looks at that guy wearing the red back there, that's Britt Schwotzer. He's normally, hey, Britt. He's here all the way from Cleveland, Ohio. He's normally my boss, except today. When I am a participating partner with Lincoln Electric. I go and teach this class with them, a lot of different events. And normally Britt's my boss, but he came here to give us a hand, get everything set up, and for tomorrow to help out with the live demonstrations. I really appreciate you taking time away from your family, Britt, to be here. All right, so we'll start with a show of hands. How many people in here have never TIG welded and have no idea what we're talking about? Well, honey, my wife raised her hand. You know, the shop isn't that far from the house, but I'm not teaching her, so anybody else who wants to know, I'll happily teach you. All right, so TIG welding, what separates TIG welding from the other welding processes? When you guys, anybody here a MIG welder, stick welder? All right, in MIG and stick welding, when we MIG and when we stick weld, our electrode is either the wire, the MIG wire, or it's the stick electrode. right, you follow me? And that is what our arc comes off of, and that's what's also our filler metal. It's also consumed in the weld process. When we TIG weld, we're going to use a TIG torch, and it looks like this one right here. Now, everybody see there's a cord on here? This cord gets to be pretty cumbersome up here, so I took the cord off it. This is not a parlor trick. It's just a lot easier. Yeah, it makes your welding a lot shorter. We're going to take this, in TIG welding, we're going to take this torch. Our electrode is right here. That's where our heat is generated. That's where our lightning or our electrical arc comes from. That's where we generate the heat into the weld plate, whatever we're welding. Okay? Our tungsten electrode is not consumed in this process. When we scratch an arc with a stick welder and we start stick welding, we consume that rod. That's our electrode and it's our filler metal. In MIG welding, when we squeeze that trigger, it squirts the wire out. That's our electrode. It's also our filler metal. And what the uniqueness of TIG is, we're going to hand feed that filler metal in with our other hand, but we can also control our heat on the fly. Everybody follow that? And the way we typically do it is with a foot pedal. So this is what the foot pedal looks like right here. So more heat, less heat. Everybody following that? Push the pedal down for more heat, let the pedal up for less heat. In your MIG welder and in your stick welder at home, when you start the arc or squeeze the trigger in a MIG gun to start squirting the wire out or strike the arc, the only thing you can weld with is what the machine is set to on the wall. Wherever you have it set, under your workbench, wherever it is, wherever you're welding. Meaning that if we don't like what we're seeing, we have to stop, go over, make the adjustments, and start our arc all over again. Sometimes if it's too far out of adjustment, we have to grind that out and start over. In TIG, it's completely adjustable on the fly, which is why in aviation, we only use TIG welding. We don't MIG weld in aviation because if something's wrong, it's never acceptable to go, oh, it's close enough. Because at 10,000 feet, close enough doesn't cut it. It has to be perfect every time. Now, obviously, I teach at a lot of air shows, so we're going to talk a lot about aviation because it is such a high standard. If you're making something for your pontoon boat or to tote your garbage cans to the street, realize you might be able to slide that sliding scale a little bit, but for aviation, it's 100% every time, or we don't do it. We take whatever that is, and we fix whatever that problem is. Any questions on that? I'm going to talk for a couple minutes about safety part of it. That arc that we talked about, we create, makes a very, very bright arc. Bright enough that it's going to burn your skin. Now the intensity of that burn is relative to a lot of different things. The kind of gas we're using and most importantly, the current that we're welding with. Obviously it makes a more intense arc. It emits light radiation. That is not gamma or alpha beta radiation, that is light radiation like a tanning bed. It will burn your skin. So when you weld, I know it's hot and I get it tomorrow. We are going to make you wear a jacket or sleeves. You can bring a jacket if you have your own jacket. But we're going to cover up all of our skin because it'll burn us. How bad will it burn us? Really, really bad. Like second-degree burns, skin peeling off if you get exposed to it at a high intensity. Now that being said, we can protect ourselves real easily by just wearing that jacket or those sleeves. We also want to protect our eyes, right? Okay? Everybody knows what this is, right? Anybody here not a welder? This is a welding helmet. Now the purpose of this welding helmet is to protect our eyes. Back in the old days, we had a welding helmet that was a fixed darkness lens. We flipped our heads down, and the moment that just covered our faces, you couldn't see anything until you struck the arc. It was 100% black because that shade in that lens inside there was so dark. Well now, thanks to modern technology, these helmets auto darken, okay? They protect our eyes, okay? Now, Lincoln makes a really good line of helmets. Now obviously, I'm pretty partial, but here's the disclaimer. There's a YouTuber out there by the name of AVE. Does anybody watch him? Arduino versus Evil is what it stands for if you didn't know. Some people don't like him, some people like him. The guy is brilliant. You can take his fabricobbling and his funny little anecdotes out of it. He is a brilliant individual. He does a very good job at a shop level for testing stuff. His thought process is right on line with proving stuff works or it doesn't work. He took these helmets. He took a Lincoln helmet and a bunch of other helmets and he set them up for testing, okay? And he tested them. He proved that the helmets that come from that company called Useless Salvage Harbor Junk, he proved that they may not protect your eyes like this. Now, obviously I'm partial. There's a lot of other companies out there that make good helmets. Speedglass, 3M, Optrel, Jackson. There's a company out there that's blue. I can't say it. Listen, all joking aside, all of those companies put a lot of research and development to make sure that they make a product that performs and protects your eyes. That's what I'm asking all of you guys to do, is to make sure you use a quality rated helmet. Has anybody in here ever been flash burned before? Okay, now you're about to see, those that are here live are about to see a lot of heads nod. Those of you who don't, let me explain to you what a flash burn is. It's a burn on the cornea of your eye that happens from the light radiation that comes out. What does it feel like? Well, imagine an angry little troll comes into your bedroom at 2 o'clock in the morning, lifts your eyelid up, and pours beach sand in your eye, then puts your eyelid back down and pats it nicely and says, have fun for the next 8 hours. That's what it feels. Yeah, he's over there laughing like that's exactly what it feels like. Now, there is nothing you can do to make it feel better. People say milk and meat, and everybody's got their own little home remedy. For about the next 6 hours, luckily your eye heals really fast. It's a burn on the surface of your cornea of your eye. It hurts, it's painful. Luckily it goes away. It's very uncomfortable in about 6 to 8 hours. Okay? So, that being said, please use a good quality helmet. Don't let people try to watch around the corner with sunglasses. Protect your eyes. A couple of features I like about these Lincoln helmets. These Lincoln helmets, it's a one-shot deal with these. The helmet, you can adjust any shade, all the way from oxy-fuel welding all the way up to arc gouging. Okay, you just the shade adjusts in here with the little dials. Also, it has a button on the side of this helmet. See this? If you push this button while your helmet is down, there's no more flip up, flip down. It turns off the auto darkening feature so you can see through it. This is ANSI rated for impact resistance. So if you have a quick grind you want to do and you want to flip up your helmet, put your safety glasses on to grind something and take it, and you put it, that whole thing, just push the button and it turns the auto darkening off so the sparks don't darken the helmet. Yes, sir, question?
Is there as much protection on number 4 as number 12?
Is there as much protection of number 4 as 12? Yes, sir. The reason is the helmet stopped the UV light. The shade is what is comfortable for your eye. You follow me? Like some people like darker sunglasses, some people like lighter sunglasses out in the sun. Everybody has that level. So that shade adjustment is for what's comfortable for you. If you're looking at it and you're like, man, it's super bright, and you're not watching the weld, you're not watching what you do. So you just darken it down a little bit to where it's comfortable, and the inverse is true. Any more questions? Yes, sir.
Some of the older auto darkening helmets that were designed for transformers do not play well with inverters.
So his question is, some of the older helmets, the very early auto darkening, don't play well with some of the newer machines. That is correct, but there's very few of them out there anymore that do. And there's one of these dials is sensitivity. So when we go to like very low current DC welding, like if we're welding something super thin, sometimes the light is not intense enough to trip those older helmets. So now we have a sensitivity or a gain that turns these eyes on the front that pick the arc flash, we can turn it up so much to the point that if you're in a room with a fluorescent light, it'll stay dark all the time because the fluorescent lights are flickering and they'll trigger the helmet. So we can adjust that sensitivity to where we need it. Yes, sir, your question.
Has the helmet technology advanced much in the past, say, 5 years?
Yes. His question is the helmet quality advanced, or what are the helmet advances in the last few years? The 4C technology, the high def technology, the old helmets, when you look through them, they had a green, kind of a greenish hue. The new ones do not. They are almost a perfect grayscale. So they're what they call 4C or high def optics. A world of difference. We have a couple of them here when we do the when we do the hands-on demonstrations. Put that helmet on and take a look. You'll see a big, big difference. It's a 1:1 optical clarity. Any more questions on that? All right. The guys that were, is anybody in here a MIG welder? How many people in here are MIG welders that use gas shielding? All right, perfect. We got about 6 or 7, 8 people that raise their hands. 9. Okay. Gas welding. When we TIG weld, we were only gonna TIG weld with inert gases. Okay? Now, what does that mean? Well, inert gases are noble gases. That's on the periodic table of elements when you're in chemistry class, right? Inert gases. Let's name them. Who in here knows the inert gases? Can name them? Name, call it out. Helium is 1. Neon is 2. Krypton is 3. Argon is 4. Xenon is 5.
Which is cheaper?
Keep going. You're not there yet.
How many more are we looking for?
I think there's 2 more. The one's important to know. That's what I'm waiting on. It's the gas weren't. Argon is not the one I'm looking for. Xenon and Radon. Those are all of our noble gas. I think I named them all. So we know that radon is a radioactive gas, right? What are we not going to use? Boop. I've been told by somebody way smarter than me that xenon is over $10,000 a bottle, so I'm pretty sure that one's out. Okay? Krypton as well. Neon is extremely expensive, so that one's out. So it leaves us 2 left. What are those? Say them, come on. Argon and helium. We're going to talk about those 2 gases because those are, relatively speaking, they're inexpensive gases and we can get them pretty easy. Now, for those of you guys who MIG weld and use MIG gas, you almost never use straight gas to MIG. You'll always add another gas in. The noble gases are what we call inactive gases. So if you're following along, it should be here, okay? Those gases cannot combine to form another compound. In other words, argon will not form another compound with the weld puddle. If you MIG weld, a lot of times you use CO2, 75-25. That carbon dioxide actually forms other compounds and helps with the deoxidation process and the wetting process in the MIG weld. In TIG, it is a 100% pure process. We only use pure inerts. So you cannot take your argon 75-25 bottle and go TIG weld with it. It is not, won't happen. Yes, sir, question? No, sir, it's an active gas. Nitrogen, nitrates, nitrides, right? So it's going to form other compounds with, depending on what we're welding, and they're going to precipitate out. We don't want to change the base metal at all. The only purpose of that gas is to keep the active gases of our atmosphere out of the weld puddle. Can everybody understand that? Oxygen and nitrogen, that's mainly what's in our atmosphere, right? We don't want that to form. Let's just say it's mild steel. What happens when you get oxygen and mild steel together? You get rust, right? Oxidation. We can take those molecular and alloying compounds and literally change them in the weld. We don't want that to happen. So we're going to keep that atmosphere pushed away with the gas coming out of this torch. Keep everything pushed away, so the only thing that's being sprayed on there, what we're going to use here, thank you, Stan, for buying us a bottle of argon, is argon. So let's talk about argon. Where does argon come from? Does anybody know? Are you a cheerleader over there, Stan? Stan's doing this. Nobody can see Stan. He's over here doing this.
Do they mine it?
No. Argon comes from the atmosphere. The way they get argon is they compress the atmosphere and they chill it. They compress it some more and chill it. And in the handout, if you look at, I think it's still in here. I might have pulled it out. I think we pulled it out. At a very specific temperature, it's about negative 200 degrees, I think. Argon becomes a liquid. So we know it, if we're at that temperature and there's a liquid in the vessel, that is pure argon. They pump that argon off, put it in bottles, and then they ship it, and then they vaporize it again and put it in the bottles that we use, our weld bottles. That's how it's transported. So the argon you're using, it's 100% recyclable. We might be using somebody else's argon from World War II today. Who knows? But argon is a repeating process. Now helium is a different story. Helium, the temperature that helium becomes a liquid is just a few degrees above absolute zero. So huge expense to try to get anything that cold, okay? It's very hard to get it there. It takes a lot of pressure, a lot of energy to get it to a liquid form. So why would we do that? Anybody know where we get the helium from?
They mine it.
They mine it. That is correct. So when they drill for oil wells and gas wells, as they punch through the surface into the cavity where the gas is, the top layer is always helium. Okay? So the oil companies control the cost of the helium. You get that? So helium's expensive. But there's a more important thing about helium. Helium is a finite resource. There is only so much of it on this planet. When we release the helium, it goes way, way high up into our atmosphere and eventually winds up making its way because it doesn't have enough weight for the gravity to keep it in. It's way up at the top. Okay, eventually I think it leaks out into our atmosphere, but I'm not a physicist, I can't tell you that. We can't basically get it again. So it's a finite resource. So it costs more. Now, how does it get in the dirt? I learned this at Bar Z Bash about 5 years ago. Does anybody know why it's in the dirt?
Radioactivity.
You're close. That's it. Naturally occurring uranium ore in the Earth's surface, as it decays, part of the decay process becomes one of the off products of it, of the decay process, is helium. So as that uranium has decayed over the last million years, it started to build up in pockets and be trapped under the Earth. So what does that, the reason I tell you that is, what does that affect? The rarity affects the cost. Helium costs about 3 times as much as argon. And we have to use 3 times as much helium to get the same effect. So we got a gas we have to use 3 times as much of that costs 3 times as much. Now you know why Stan bought a bottle of argon for today, right? Right? But helium has one property that we love. Helium, we say burns, understand it doesn't burn. It creates a 1.7 times hotter arc than argon out of the same machine. So as makers, fabricators, repair guys, whatever we are, our whole group, how does that help us? Say that out loud, loud. Thicker castings. Think cylinder heads, intake manifolds, wheel castings. Aluminum is a high thermally conductive material. It loves to get rid of heat. It loves to conduct heat all throughout it. So you've got to keep a ton of heat in it to keep it molten to 1200 degrees. That's about, pure aluminum melts at around 1200. So we got to dump a ton of heat in it. All right? If this machine simply switches to helium gas, we can do 1.7 times more work just by using helium in it. But we got to use 3 times as much of that gas, and it costs 3 times as much. So unless you got a lot of money, we're probably going to use argon most of the time. Yes, sir, question?
What about hydrogen? I know you get hydrogen brittle in your weld, or
Hydrogen is a very reactive gas. When it gets hot, it goes boom. So we can only use inert gases. Hydrogen is not an inert. When hydrogen sees heat, it burns, combines with 2 oxygen molecules, and makes water. So if we can just figure out how to separate that water molecule apart, it's a never-ending cycle.
Hydrogen has another very dangerous property. It is lighter than air, and it would fill the entire tent up here until it found something
To make it go boom.
source of ignition down here, and that tent would just go straight up.
So for those online, you probably can't hear what Stan's saying. He said hydrogen is lighter than air, obviously the Hindenburg, right? Lighter than air. And if we were using it, the gas we would not be using would fill, and then until it found an ignition source, and then we'd find this tent 3 counties over.
Over on the other side of the mountain.
Yeah. Any questions on that? It's only inert gases. It's going to be helium and argon. Argon primarily. Any questions?
So you're saying we should get just the straight argon and get away with it?
Straight argon is always going to be the cheapest. It's going to be the least expensive. Okay? You can blend helium and argon and get some of the properties of the helium out of the argon, but why spend the money unless the process you're doing requires it? Why do that for day-to-day operations when the argon will get the job done for you? He has one heck of a good question. Go ahead.
I'm the lucky guy who wins that TIG and I walk out of here today. What's the least expensive way I can acquire some cylinders?
Okay, so his question is, what's the least expensive way I can buy cylinders? Facebook Marketplace or Craigslist. Don't buy somebody else's rental bottles. Realize there's rental bottles and owner bottles. Don't go buy a rental bottle from somebody because they just took your money, because that bottle, when you go to get it filled, belongs to whoever's name is stamped on it. So used, I will say used bottles that are not being used by their rightful owner is probably the best way to do it. Stan, you have a question.
Can you talk just a shade louder so the folks in back can hear you? Just elevate your voice a little bit.
I don't think I can talk any louder.
Your wife says different.
Honey, just make me mad. I can talk really loud. All right, I'm trying. If you could get everybody back there to shut up, we'd be great. Kidding. Kidding's a joke. All right, did that answer your question, sir?
It did, sir. Thank you.
Unfortunately, the bottles are all over the place. You can find them for $250. Some places want to charge you $450, $500 for a 1-hour bottle. Question.
Now, how do you keep argon from leaking out of the bottle?
How do you keep it from leaking out of the bottle? Turn the valve shut.
As high as I can, but I'm getting some bubbles on it.
Okay, then the valve is bad. It needs to go back to the gas supplier, and they need to replace the valve. There should never, argon will not leak out of the bottle if it's working properly.
Now, can you take the fitting that goes in the screw in the thing, and then you clog that up, seal up, and then tighten that so that it fits on the fitting of a dummy? Instead of going, let me rephrase it. When you take and put your regular on your argon, you have that fitting that fits in the bottle. Can you take that fitting and seal it up and then screw it in tight?
So I think what you're asking me is, can you put a plug in the hole? Well, they do make a plug that goes in there. It has O-rings in it and fits correctly. But realize that the pressure coming out of that bottle, if it's leaking out of that stem, and you put a plug in there, eventually those two pressures are going to equalize. So you have 1,200 pounds of pressure behind that plug, or whatever's in that bottle. So the right answer is take it to the supplier and say, hey, this bottle that you've sold me, rented me, whatever, is defective, and they'll change the valve out for you. They'll pump it down, change it out, fill it back up for you. The way we measure gas, just so we can all talk on a level of understanding, is measured in standard cubic feet per hour, whether it's argon or helium. Just to give you an example, we do about 15 to 20 on argon, and 45 to 60 on helium. So see, it's 3 times as much helium. That's kind of that spark when you get the machine, you go home, you're kind of setting it up. That's where you would start. Sometimes we can crank it down a little bit. Sometimes we need to turn it up. That's kind of the middle of the road there. Okay, yes sir, question.
Do you use a different regular
No, sir. Same regulator. He asked, do we use different regulators? No, all one regulator. It's an inert gas, it can be measured. There are regulators with gauges on them that just, you know, there's a gauge and it says standard cubic feet per hour, you adjust it. And then there's actual flow meters with the little tube and the ball. The tube and the ball is more accurate. But for most of us at home, our home shop building hot rods, that accuracy is not needed. What we need is to make a good weld. And most of the time we can look at our weld and say it's correct. If you're going out to do specification welding, aviation welding, then you will always find the flow meter, because this weld spec sheet will tell you you have to flow this much argon. And if you change that, you're now welding out of specification. The engineer has to either recertify the weld you did, or you have to go grind it all out and start over. Does that make sense? Yes, sir.
We've got a flow meter, and one side of it has an argon measurement, one side has CO2, and they're a little different.
So, yeah. So the density of the gas is different. His question is, on the flow meter tube, there's different scales. One says argon, one says helium, one says CO2, right? But the density of the gases is all different, so it will take more volume to achieve that. Does that make sense? It's fitting through a smaller hole. More gas can fit through a smaller hole. Stan has a question.
Good. William and Betty wants to know what amperage breaker that TIG 200 runs on for their garage.
William and Betty, thanks for watching, William and Betty. I will tell you right now, I think it's a 30. I don't have my glasses. I can't read it. I think it's a 30.
I can tell you I've run one on the 30.
Yeah, I'm pretty sure it's a 30 amp breaker. It's on there, but the print is so small.
240 or 110?
So the TIG 200s, we're going to talk about them here in a little bit, but they're multi-voltage machines. So you can run this machine on 110 volts or 230 volts. Here's the disclaimer: you will not get full kVA out of the machine at 110. The reason why is everyone's like, why not? I don't understand. It's simple Ohm's law. There's not that much wattage there. You take a 20 amps times 110 volts, it's 1,200 watts. That's it. That's all you're going to get out of it, period. 230 volts times that is double, 2,400 watts, okay? But most 230 volt services are 30 amps, so you add 30 more amps into or more amperage into the circuit. You get full output at this machine. Any more questions? Did that answer their question? I have welded 1/8 inch all day long on 110 volt, good 110 volt, not through a little tiny extension cord through the neighbor's yard, but a good 110 volt. I've welded 1/8 inch aluminum all day long with this machine. That's what we teach with at Oshkosh. We have 110 volt there.
Those are low-end steel welds. Can you use stainless steel?
You can do any, we're getting to that, but I appreciate the answer. We'll get to that in a minute, but he asked, can you weld anything? And the answer is any weldable alloy we can weld in TIG. We're going to talk about that in a minute, okay? Torches. There's a reason I teach this. My local, where I live, my local Lincoln rep has asked me a couple of times. I live very rural, or I did before everybody started moving to Florida. Very rural, and sometimes somebody will buy a machine and they'll be like, I'm having trouble with it, and they know that he knew that I was in the area. He said, hey, would you mind swinging by this customer's house? He says there's something wrong. I need to know if the problem is the welder or the welder. Joke there, right? Is it a human error? Is it a problem? Both times I've ever done that, it's been a human error, and it's been a problem with the torch, because a lot of us get excited, we want to go home, we want to try this out, right? But nobody's ever taught us this. This is pretty simple. This is the TIG torch is going to come in the machine. It's going to look very similar to this one. In the back of this TIG torch is a couple of parts that if they are not correct, you won't be able to weld. No matter how hard you try, it's going to look like a bird, probably a seagull, flew over and had a little accident right over your weld. Anyone weld like that in here? Be honest. Stan, why'd you raise your hand? I've seen your BattleBot welds.
Everyone has bad days.
Okay, everyone does have bad days. All right, let's go over these torch parts. They all perform a function, and they all have to work together, and if a couple of them get out of sync a little bit, they'll cause you problems. Now, All TIG torches work the same. There's different sizes of torches. This is a 9 torch here. Just going to show you the parts of it. All of them work the same. This piece on the front is called the cup. Everybody see that? It is made of ceramic just like a coffee cup. It is exposed to high heat. The ceramic cup does a couple of things. It keeps all the argon gas around here and lets it come out the front. This is made of the same kind of ceramic as a coffee cup. If you drop your coffee cup on your shop floor, what happens? You got to get more coffee. Yes, it shatters. It is a consumable that will break if you drop the torch. Now, there's lots of different styles out there. Most of you guys are YouTubers, so you guys, anybody in here follow Jody Collier, Welding Tips and Tricks? He's an amazing guy, wealth of knowledge. He's been a friend to me, great guy. When he says it, you pretty much can believe it. Whether you don't like his technique or not, that's not really up. I promise you the guy can weld. I've seen it firsthand. He talks a lot about on some of his videos about the see-through Pyrex cups. There's several different variants of them. What are they? Just imagine this on a Pyrex, like a Pyrex mixing bowl, okay? You can see through the cup. People think it's great. That's wonderful. They cost about $35 a piece. And the second that 2400 degree piece of Pyrex touches your cool metal workbench, guess what happens? You just wasted 30 plus bucks. But they work, there's nothing wrong with them. But they're expensive. You see all those kids that were up here earlier? I gotta feed those kids. So if there's a way I can save money, I'm going to do it, and I think that most home people, that's what they're after. These cups work great. There's nothing wrong with them. Now, anybody in here follow the FUPA cups, the Furic cups? The Furic Corporation makes the FUPA cups. They are great. I got them at home. They work. They are made out of a ceramic type material similar to these. What are they? They just have a bigger hole. They're for doing stainless steel. They help diffuse the argon better. Okay, but do you need to go out if you buy a TIG machine on the Barzy Bash deal and go spend all that money on extra stuff? No. I promise you, there's bombers that fought during World War II that were TIG welded with something very similar to this. Okay, if we could send bombers all the way to Europe and back during the war safely without weld failure, okay, let's talk about that at a minute. How many people in here have Heliarc welded before?
I don't have a Helium stick rod, right?
Nope. Has no one in here has Heliarc welded before? Anybody ever heard of it? Okay. Does anybody know the difference between TIG and Heliarc? Who said it? Yeah, he's correct, and somebody else said it back there. He said proprietary name, somebody else said nothing, both of those are correct. The Linde Corporation, just before World War II, and this is just an interesting fact, figured out that they could use helium gas in an arc to make a highly repeatable, very high strength, high quality aluminum weld. The Linde Corporation took it and trademarked it Heliarc. So unless you can find an old Linde TIG welder somewhere stuffed in somebody's closet, you've not Heliarc welded. Oh, you've got one? He's got a Linde. Good for you, buddy. Those were good machines. They were big. Well, all the machines were big. We'll talk about that coming up. Yeah, it takes up a lot of real estate in your shop. So we call it TIG. TIG and Heliarc is the same thing. The American Welding Society calls it GTAW, gas tungsten arc welding. It's also the same thing, but they like to call it their own specific name. It's TIG. Okay? Let's go back to our torch. You got a question, Stan?
Rick O wants to know, is this square wave only?
Is this square wave only? Yes. An AC, it would be square wave only.
But that is also a DC machine.
Yes, but DC is, you're not in a waveform then. So this question was, is it square wave only? I assume that you mean, can it make a sinusoidal waveform? And the answer is no. You cannot in these machines make a sine. But I don't know why you would.
Just asking will go AC and DC.
If he's asking AC and DC, yes, it's AC and DC machine. But does it have an ability to take the waveform and make it back to sinusoidal? No, not on this machine, but I don't know why you would. We'll talk about the square wave coming up. Let's go back to the torch, okay? The front of the torch has a couple of things. Now, most folks that are here with us today are machinists, right? This is the tungsten. Remember, this is actually my torch from home. So you notice the tungsten's small, and it looks like I might have drug it behind my tractor, but you know, you gotta stretch the dollar, right? This is my tungsten. The way we hold this tungsten, which is our electrode, is with a collet. This collet looks very similar to the collet that will go in a Dremel tool. Everybody follow that? In a Dremel tool, there's that little collet, you got the little tiny little wrenches, you tighten the little cutter in there. This works the same way, with one exception. We don't go to make sure that thing doesn't come out at a bazillion RPM. These are finger tight only because this collet is made of copper. The reason it is made of copper is for conductivity and heat dissipation. This tungsten, and we'll talk about this more in a little bit, is going to get really, really, really hot. We want to dissipate that heat into this torch. This particular torch is an air-cooled torch. It is not cooled by air, but it's cooled by argon, and since argon's in the air, we call it air-cooled because it makes more sense, okay? There are water-cooled versions of these torches. They have two little tiny hoses that go in there. They run water around to a little tiny radiator that sits on the ground. And people say, well, do I need a water cooler? Well, it's relative to what you're going to do. If you're going to TIG weld on a bench all day long, I would invest in a water cooler. Most of us are hobbyists. We're making things, and that torch has that downtime. You make a weld, you set the torch down. It's cooling down the whole time you're there, so you don't need it. If you're welding aluminum or some nickel-based alloy where you're using a ton of heat and you're welding all day long, the torch will start to get hot in your hand. Okay, because it's dissipating that heat, which is why this collet is copper. It dissipates that heat off the tungsten back into here and aids in cooling, okay? Now, we're gonna spend a few minutes at the end talking about tungstens. So if anyone has questions about tungstens, hold them till the end. We'll spend 15 minutes talking about tungstens, okay? Tungsten's our electrode. This thing that it fits in is the collet body, or in this case, the gas lens. I have a collet body up here. This is a collet body. This is a gas lens. They are interchangeable, okay? The collet body is what we've been using since World War II time. We started off with this heliarc welding. The purpose of this is exactly the same, but one does it better, and I'll explain in a minute. The collet body has holes in it. Can everybody see those holes? No. All right, well, I'm getting to that point too. I can't hold it far enough to see them. There's little holes here around the surface. And what happens, I don't know if this is the right size it should be. This tungsten's gonna stick out of there like that. Everybody see that? The gas is gonna come out of these holes around here. There's a ceramic on there. That ceramic forces that gas to come out here. It cools this copper before we use it for welding, and it protects that tungsten from the atmosphere. That tungsten can get up above 5,000 degrees when we're welding. If it touches the oxygen even for a second, the tungsten is junk. I mean, we gotta go clean it. You can't use it for welding anymore. Now, why do we have this and this and get confusing? Let me make it clear. Think of this. Everybody has gone in their sink in their kitchen or their bathroom at some time and had to screw that little screen off the bottom and get the gravel and the grit and stuff out of it, right? And inevitably, you turn the sink on and to rinse it out before you put it back on there. Everybody done that? And when you turn that water on, your pants always get wet because the water sprays into the bowl all kinds of crazy directions, right? All different directions at one time. Hits the bowl, splashes out, gets you wet. Like right now, my drawers are wet, right? Well, that is your kitchen sink without the screen in it. So that gas comes out of these holes and hits the side of this ceramic inside, like this, and it comes out and it's turbulent, and it's whipping around. Now, you take that screen in the kitchen sink, you got it all cleaned out, you screw it back on there, and you've got that nice column of water that comes out, right, to fill a pot with. Nice laminar column. If you look in the end of this, there is a screen. That screen does the exact same thing in your kitchen sink. It is basically a laminar flow generator. It just keeps that, slows that gas down and gets it out coming in as a column. Well, why do we even care? Well, there's a reason. If we were sticking a tungsten out and we were using a standard collet body, we could probably get away with sticking that tungsten out about that far. Any further than that, and that gas whipping around will whip oxygen in, and that oxygen will hit that tip. And when that's 5,000 degrees and oxygen hits it, the tip is ruined. You got to take it out and regrind the tip. And we'll talk about that in a few minutes. Okay? Well, why would we want to stick that tungsten out that far to begin with? Anybody know?
Into a corner.
Very good. Think of a race car roll cage, right? You got that joint that comes together. You got to get down in that joint, right? You want to stick that tungsten out so you can get that heat in that joint, weld that joint. If we simply switch to a gas lens, we could probably get away with sticking that tungsten out about that far. All right? Now, it's a bit of a stretch, but I want you to understand the difference. Now, the gas lens also does something for us on our welding. We have our weld material here, whatever we're welding, our plate. We've got that gas coming out over, and it's going. Remember, argon's heavier than air, right? It is. It's heavier than air. So the argon's going to cover what we're welding, and it's going to hang out there for a second. While that piece is cooling down, the longer it hangs out there, the more it protects that weld from the atmosphere. If we make it turbulent and it's whipping around there, it's entraining oxygen into that column of gas, it doesn't give us as good a coverage. Now, steel and aluminum aren't quite as touchy. If you go to the nickel-based alloys, Inconel, titanium especially, it hates oxygen with a passion. The second oxygen hits it, the nickel-based alloys will turn black. All right? So, do you have to use a gas lens? No. A lot of the torches, the machines come with gas lenses in them. They're not extremely expensive to add on. Why do we even use the collet bodies? That question comes up all the time. This is the collet body. This is the gas lens. Okay, can you see them? I know this is for a 17. It's a different size, but it's all I have. And I have to bring all this stuff from Florida, okay? So, see this? Cost, we'll call it $1.50. See this? 15 bucks, okay? So now imagine, I got a lot of friends that teach at the Lincoln Weld School up in Cleveland. Charlie the Rich, how you doing? He's up in Cleveland. Hopefully he's watching me right now. Probably not, he's probably teaching. Imagine that you have 120 students. You run 3 classes a day, a morning, an afternoon, and an evening class, right? Every student, when they're learning, is going to wreck stuff. If you wreck a $1.50 item while you're learning, it's a whole lot less cost than every student wrecking a $15 item. And as a beginner, it doesn't help you anymore. It helps you in the end, once you start to learn how to do it. Okay? This does not aid you in learning torch angle and foot pedal, how to throttle your foot pedal and how to feed the filler metal in it. This doesn't help you. This helps you later down the road. Question?
Two, kind of on the same theme. How do you know if your gas lens is wrecked, and how do you know if your tungsten got oxygen?
I'm sorry, ask one question first. Let me see if I can answer it.
Sure. You talked about the students wrecking gas lenses. How would you know your gas lens? Let's say
He said, how would I know that I wrecked my gas lens? The whole little screen in the end is all melted into one little blob. How would I know if I wrecked the collet body? Because there's a big ball of copper stuck on the end.
Well, how would I know if I got oxygen on my tungsten and I need to
You will know instantly whether you got oxygen on your tungsten because it gets a big warty end on it. And we're going to talk about tungsten preparation. It should be a nice point when we're done grinding it. Any other questions? All right, we'll get back to the torch again. We're gonna put some parts back in here because we took them apart. Here's the collet. Okay, collet body. Put them back in the torch like this and screw the front on. Now the back of this torch comes off. This is called the back cap. The back cap serves a couple of purposes. It protects the full-length tungsten. This is a full-length tungsten. When this tungsten is in here, it's in the back. Remember I told you this tungsten can get upwards of 5,000 degrees when we're welding. At that temperature, if oxygen hits this, the tungsten starts to oxidize. It's what we don't want to happen. So we protect it with this. This is intrinsically sealed. This is made of a Bakelite type plastic. Is anybody old enough to remember Bakelite? Right? Well, we know you're old enough, Stan. Bakelite type plastic. That means it's somewhat brittle if we drop it against the concrete floor. Here is what I wanted you to understand. I have been to many, many shops, including my own, and found cracks in this. And the crack a lot of times will run along the edge here, and you don't see it. What happens is you make a basic carburetor. It's a Venturi effect. As the gas comes through and starts shooting out the front, it starts sucking oxygen in the back, and you swear that this Lincoln welder is not worth a hoot. And really the problem is right off the bat, you drop this on the concrete floor. Okay? So if you got problems, you can't figure out why the weld's turning black and warty and everything, take a look at this. But while you're looking at this, this is the numero uno failure point. See that little red O-ring there? Can everybody see it? That red O-ring stops the argon gas from coming out and stops the oxygen from coming in. That is the sealing point. Now, remember I told you this torch gets warm when you're welding with it. It gets pretty warm. You could pick it up with an ungloved hand, but it can be uncomfortable. It can get that warm, okay? When this screws into there, that O-ring, because this torch gets hot, that O-ring gets hot. And when you screw this off because you're angry because you messed up for the 75th time your tungsten, and now you got to take it out to the grinder to grind it, and you don't notice that that little O-ring dropped off and fell on your shop floor. You put it back together, then you throw the torch down, and you're like, I can't do this, bad day, dog snarred it, whatever bad words you choose to say. You realize the only problem is that little red O-ring is now sitting on your shop floor. Both cases that I had to go out and help my local Lincoln guy troubleshoot a problem, the O-ring was on the shop floor. That's all that was wrong. Now, that being said, inevitably, when that O-ring falls off and drops onto your shop floor, it will be a Saturday or a Sunday or a Friday night where you cannot go to the weld supply. And most of you are problem solvers and goes, oh, wait a minute, I know I've got some O-rings in a drawer over here somewhere. And they're black. And you put that little black O-ring on there and you screw it on. That O-ring is made of like a butyl type rubber. Guess what happens at about 225 degrees? There's a brief flash as the vapor cloud comes out the back. There's a brief flash, and then there's a hot, sticky mess of melted black O-ring. That O-ring is a special silicone O-ring. It takes a lot of heat. I might be speaking from experience. Those O-rings are not expensive. They're usually less than $1 at the weld supply. So if you get into this and you're starting to do it, pick you up a couple, just put them in a little Ziploc bag, keep them around, because you will drop one. They will come off. That being said, if you notice that there is one here without an O-ring on it, that is because my torch from home, when I was setting up this morning, I realized there was not an O-ring on it. So I had to go take an O-ring off the welders over there for the class so I could show you the O-ring and where it fits. Now this O-ring goes in here, or this back cap goes in here and it screws in. When you tighten this back cap down, it is not the monkey fist of death, okay? Fingers. When you tighten it like this because you're afraid it's going to come loose, that little copper collet crushes, and then it's no good. And then sometimes you can't get it out of the torch because you made like a swage, and it swages up in there if you go crazy. all right? Tighten it down, a little tight, a little snug like that to hold the tungsten in place. There are different sizes of back caps. I want to point that out. People always ask, notice this back cap is shorter than this one? Well, this fits into tighter places, right? They have one that's called a button back that just looks like a little button and it screws on there. Does anybody have any idea why we don't start welders off with that?
You waste a lot of tungsten.
He got it. You waste a lot of tungsten. This tungsten comes in this length, okay? Tungstens can be inexpensive, too expensive, depending on what you have, right? But at minimum, these things are $4, $5, $6 a piece, okay? Even for the inexpensive ones. You got to cut it in half or in a third to get it to fit in here. But then as a beginner, you're messing up every 3 to 4 minutes and regrinding it. And as you regrind it, you can only regrind it so small and it won't fit in the collet anymore and stick out far enough. So you wind up breaking this thing up into pieces and you have all these unusable pieces. Myself personally, if you notice, from my torch at home, mine is that big, okay? It is graduated down to the point where I've ground it down enough times that this will now go into my box eventually. And when I go to a halfback or a quarterback, what we call these, and that's not the one that throws the football, by the way. It's a bad joke. Come on, help me out. You guys are falling asleep on me. Yeah.
Okay, tell it again.
Oh. Back cap. Back cap. This torch fills this little hollow chamber inside the back cap. This torch fills it with argon. So no matter how hot this gets, it never touches oxygen. Does that make sense? Everybody? Any questions on that? You doing good over there, Stan?
I'm good over here. I'm answering the ones I can.
Any questions so far? All right. Let's talk a minute about remote control devices. We said earlier that this foot pedal is how we like to teach this. Does anybody know why? For those that have tuned in and didn't watch in the beginning, this foot pedal in TIG is how we typically like to control our heat. Meaning the more you push on the pedal, the more heat the machine will give you, up to whatever you set the machine at. Here's an example. If I set the machine at 50 amps, when I floorboard the pedal, it gives me 50 amps. Half of 50 is 25. So if I give half pedal, it's 25. So a half pedal makes a 25 amp adjustment. That is why we recommend setting the machine to only the amount of current you need to make the weld. Because if we only needed 50 amps, 25 amps is half pedal and 12.5 amps is a quarter pedal adjustment, right? So we have very fine adjustment of our heat. If we set this machine to 200 amps and floorboard it, we get 200 amps. Half of that is 100. A quarter pedal adjustment makes a 50 amp adjustment. It's too hot, too cold, too hot, too cold. You can never make the little adjustments that you need to get the heat right where you want it. So don't just turn the thing all the way up and think you're going to control it with a foot pedal. It takes the adds sensitivity into the foot pedal. It's so sensitive you can't keep the heat where you want it. Questions on the foot pedal? All right, there's other remote control devices. If you guys are following along in the handout, it looks like this. Okay, this is a hand amp troll. There are also switches. There's everybody's design in a hand amp troll, what they like. Different companies, there's the ones that slide, there's ones that are like a little tank track you turn, little wheels. Doesn't matter, they all do the same thing. They tell the machine how much current to give you. If you want to learn to cuss like a sailor in less than 15 minutes, put one of those on your welding machine. Now, why do we have them? Anybody know why we would have something that's so difficult to use? In an awkward place is not wrong. Think about this for an example. Now I'm from Florida, it's a free state. We are not OSHA controlled. We are OSHA influenced, not OSHA controlled. There's a difference, okay? If you were in a process plant, think a milk plant, right? And you're up there on the top of the plant somewhere welding some stainless steel tubing. I know it's a little bit of an exaggeration, but you'll get the point. You're welding the tubing. You're on top of a scissor lift, but you can't quite get up to the peak up there because the scissor lift won't go up high enough to get your head up in there, right? So what does everybody do? They grab a piece of scaffolding, an apple crate, they grab a step ladder, right? They're gonna go put that step ladder on the scissor lift. You guys know I'm not lying about this. There's what you're supposed to do, and then there's the reality of what people do. Right? So they're standing on a step ladder on top of a scissor lift trying to do a sanitary weld on this pipe, and they got a foot pedal. So now they got a foot pedal standing on one leg with a ladder trying to balance, right? It's out of position weld. The guys that do this are amazing. I say guys, I mean that is the guys and girls, because the industry's being taken over by some amazing female welders. It's a very difficult skill to learn, but it's necessary if you're going to do that kind of welding. The reason I bring that up is somebody inevitably asked me a question about a button control or a hand control, so we've talked about it. Everybody good on that?
A lot of World War II aircraft were done with
Absolutely. Built all our battleships for us too.
I actually learned how to use a foot pedal right there on my elbow.
Stan says he learned how to do the foot pedal on his elbow. That's why he's got biceps on one side.
Left-handed arm wrestling later.
So I've used a concrete block. You know, if you have to get out of position, you just put a concrete block, lay on your back, weld. Don't weld underneath what you're welding. Can anybody see why that's a bad idea? To the side? Okay. All right. In TIG, can anybody tell me, and you just call out the alloys we can weld in TIG welding? What are they? What different metals? Stainless, titanium, aluminum, Inconel, mild steel, cast iron. If it is a weldable cast iron, not all cast irons are weldable. We could spend 4 hours talking about how much everybody hates cast iron and why it's a bitch to weld, but we'll, okay. That is correct though, weldable cast irons. Magnesium.
We've seen him do it. Green Hornet.
Yeah, the Green Hornet. What else? Inconel, Monel, Hastelloy, copper, brass, bronze, nickel. The correct answer is any weldable alloy can be welded in the TIG process. Now notice that the giveaway there is weldable alloy. What is a non-weldable alloy? No? I'll answer the question with a question. Anybody ever wonder why we still rivet airplane wings on airplanes?
7000 series aluminum.
It's 2024 aluminum. 2024 aluminum is a non-weldable alloy. Now I know there's somebody out there in the YouTube world who's going to try to tell me I'm wrong, but you cannot make a strong weld in 2024 aluminum that will pass. Yes, you can stick it together, but you can also break it. You have to be able to certify that weld. Now, 2024 aluminum, we put alloying properties in there to give it its ability to be shaped. Think of the engine nacelle around an aircraft, right? There's a lot of curves in there. We're taking that metal and stretching it to crazy extremes. So it's all kinds of compound curves and twists and everything in there. To allow that aluminum to not work harden and twist it, we have to add alloying elements in there. Those elements make it unweldable. Most specifically, and I know because we're all the inquisitive minds, in 2024 I've been told it's because of the copper. There's a lot of copper in it. And copper has an extremely high melting temperature and aluminum has a low melting temperature, it's like 1200. So when you make the weld, they separate out. That you'll never get the aluminum hot enough to melt the copper. Now how they put the copper in there, that is way above my pay grade. I'm sure somebody out there in YouTube world knows. Ask AVE, he knows everything. But that's why not all alloys are weldable alloys. But anything that's weldable, we can weld in the TIG process. Now here's where it gets confusing. How do we know whether to TIG weld that in DC or AC? You have
want to interject something. There's a gentleman in chat. His name is Machine Tool, and he is literally translating everything you're saying and turning it into Spanish and putting it in chat,
Thank you.
which is helpful. So
Yes.
say thank you.
Thank you, Machine Tool. Is it? Who is that? Just his handle, or is that his YouTube channel?
That's his YouTube channel. Just says Machine Tool.
Tell him. So there's somebody on the live feed that's taking everything I'm saying and they're translating it into Spanish, typing it in Spanish, so that the folks that don't know English can do that. I appreciate that very much. Unfortunately, I don't know much Spanish. Usually there are only bad words in how to order a beer. So I'm trying to think of where I just was. DC versus AC. Thank you. DC versus AC. How do we know whether to weld an alloy in DC or AC? Anybody know?
How it handles heat.
Nope. But how do we know what to set the machine to? I'm going to tell you this. I am a self-taught welder. I started out when I was his age, which is about 13 years old. I bought my first welder. I learned everything the hard way. There wasn't YouTube and internet, and I mean, we had beta tapes then, okay? That tells you how old I am, okay? So the only way you learn was either to have somebody teach you, go out and do it yourself and figure out what you did wrong, or hopefully go to a welder and he would bring you under his wing and teach you, which I did pretty much all three of those, okay?
Aluminum AC.
Well, there you go. But I'm going to teach you the keep it simple, stupid method. If you think of every one of those elements have they're in a coupon, right? A little weld test coupon. Every one that we talked about, the aluminum, the magnesium, the Hastelloy, Monel, all of them. You have this pile of them, right? And you're going to put them in two piles. One pile is DC, one pile is AC. Put them in two piles. You can put every single one of those elements in one pile except two. They'll all be in the DC pile except two. Does anybody know what they are? Aluminum and magnesium, that is correct. Aluminum has an ugly brother called magnesium. Okay? Aluminum and magnesium we weld in AC. Now I know the folks that are out there that watch Jody, yes, you can do some very hot rod welding in AC on, say, cast irons. Yes, that's true. Remember, this is a basic class where we get way past basic, because most of us in here are already thinkers. But for the basic principle, everything is welded in DC electrode negative, and I'll explain that in a minute, except two, aluminum, magnesium. We weld those in AC. Does that clarify it for you? When I learned this, it took me years to figure this out. Years. All right. Why is the polarity important? Well, if you take the arc that we make with this torch and you measure the dead center of that arc is around 10,000 degrees. Okay? We're going to use that round number because I know somebody's already Googling it. Use that round number because we're going to do math with a number, and 10,000 is a lot easier to do head math. Okay? If we basically have two types of electricity. Granted, we're a little bit oversimplifying it, but for the sake of this argument I'm about to make, it makes sense. We have DC and AC. DC stands for direct current, AC is alternating current. Realize, think of a car battery in your car. Everybody's had to jump start a car or seen a battery jump started sometime in their life. There is a red jumper cable that goes on the positive. There is a black jumper cable that goes on the negative. Negative and positive. The reason the battery is typically dead in the car is because somebody left the lights on their old 1980s vehicle, right? It doesn't turn off automatically. The lights went dead, the battery went dead. That battery gave up all of its energy and the electrons flowed in one direction continuously until the battery died. But we had a positive and a negative. All batteries, regardless of what they fit in, are DC. Watch battery, cell phone battery, tablet battery, computer battery, car battery, airplane battery, they're all DC, a direct and constant flow of current until the battery has given up all of its energy. For those of you who know what I'm about to say, you'll know where I got it from, but all the angry pixies went in one direction. That's an AVE saying. Okay, the inverse to that is alternating current. Alternating current does not have a permanent positive or negative. Positive and negative switch back and forth constantly. Here in the United States of America, it's 60 times a second. If you go buy anything from Walmart that plugs in the wall and you turn it over, take it out of the package, it takes you 15 minutes to cut it out of the package, and look at the back of it, it says 110 volts, 60 hertz, right? That 60 hertz means that 60 times a second, the positive and negative are changing direction back and forth. Now, this is what it looks like if you're following along. This is a sinusoidal AC sine wave. When it's up here, it's positive. When it's down here, it's negative. I'm going to talk about this a bit more in a minute, but I want you to understand that waveform keeps repeating itself. Positive and negative, and AC switch back and forth. Let's go to that DC for a minute. Remember I told you it's a 10,000 degree arc when we're in DC? 10,000 degree arc in AC, it doesn't matter. But we're talking about DC. That arc is 10,000 degrees. If we take those jumper cables, we've got them hooked to the battery, right? Imagine we bring it over here, and our TIG torch, we take the tungsten, and we hook the tungsten to the positive to the tungsten and the negative to what we're welding. We call that DC electrode positive. Yeah, I'm trying to help the folks online follow where it is. DC electrode positive polarity. 30% of the heat we generate will be in the plate. What are we welding? Doesn't matter, the plate. We call it the plate. 30% of that 10,000 degrees is in the plate. How hot is the plate? 3,000 degrees. Remember, it's 10,000 degrees, 30%. 3,000 degrees is in the plate. 70% of the heat is in the tungsten. How hot is the tungsten? 7,000 degrees. Tungsten, pure tungsten, if you're taking notes or you're at home, you want to take notes, pure tungsten melts at about 6,280 degrees. How hot did I say the tungsten was? What happened to the tungsten? Turned into a ball and dripped off the end. It's gone. As well as your torch, typically, because your torch can't get rid of that much heat that fast, unless it's a brief period of time. Okay? That's the reason we never TIG weld in DC electrode positive. That is the reason we never TIG weld in DC electrode positive. Any questions about that? We TIG weld in DC electrode negative because the inverse of what we talked about now becomes true. 3,000 degrees of heat is in the tungsten. 7,000 degrees of heat is in the plate. How hot is the tungsten now? 3,000 degrees. What temperature did I tell you it melted at? 6,280 degrees. So that tungsten can take that 3,000 degree temperature range, right? Does that make sense? There's a question online.
Would you care to talk about why we have different sizes of tungsten, why we need them?
We're going to talk about tungstens at the end. I got a whole section on tungstens. Yes, sir.
Is it possible to set up those machines in the wrong configuration?
Absolutely is. And I'll explain why. Give me just a second to get there, though. Are there any questions on that? His question was, is it possible to hook it up in the wrong configuration? Yes. The reason is, this is a dense connection. It is a quarter turn. Stick it in and turn it. Stick it in the ground and turn it, right? So we can stick. Now, Lincoln makes it pretty simple. There's a picture of a TIG torch. That's not the ground, that's the TIG torch. And this one has the ground clamp. That's the ground clamp, not the TIG torch. So it's pretty, picturesque, simple, but everybody's done it that's welded a lot has got them hooked up backwards for the first second, couldn't figure out what the heck was going on. Why would we want to be able to hook them up backwards? Anybody know the answer to that question? Stick welding, thank you very much. Both of these machines are excellent stick welders. Why is that? Well, when we weld, In TIG, it's a constant current application, meaning that where we set that foot pedal, wherever our foot stops, the machine will produce exactly that much current as long as we keep our foot there, right? Constant current. When you stick weld, you go over to your old stick welding machine and you set it on 90 amps, stick the electrode in it, strike the arc and start welding. That machine will give you 90 amps because you set it at 90 amps. They're both constant current machines. MIG is constant voltage machine. It's a completely different process the way it happens. Okay? So since this is a constant current machine, it already has a stick welder built in it. So when you buy these machines, they come with stick electrodes. It does a beautiful job stick welding. They're very stable, a very stable arc in it to be able to TIG weld. So it gives you a very stable arc to stick weld. Yes, I'll get back to that in a second. To further answer your question, typically when we stick weld with DC electrode positive. So we got to be able to plug that stick stinger into the positive side. Does that make sense?
It does.
All right, he asked 60-10. 60-10 rod to whip 60-10. I'm assuming you're talking about to whip it, to be able to whip it. Not to get off on another subject, but just to try to answer it. 60-10 is typically used for root pass on pipe. It has the ability to draw a very long arc and come out to keep the puddle cool. And machines have to have a 60-10 setting, inverters. Yes, they will run 60-10. Any other questions? Yes, sir.
Yeah, can you weld stick rods with AC?
Yes. The question is, can you weld stick rods with AC? And the answer is yes, you can. The rod has to be specific for the AC. Any more questions on that before we get into the whiz? We're getting ready to get into some AVE science here, so y'all better hold on. Okay. We already said we're only gonna DC weld and DC electrode negative, right? AC, if we go DC electrode positive, it's gonna smoke the tungsten. So that's out. But we need to be able to weld an AC. Now, why do we need to weld aluminum and AC? The cleaning. I'm getting some looks. The cleaning. Aluminum has a lot of properties we really, really, really like, but one of those properties that we like makes it difficult to weld. Aluminum oxidizes instantaneously in the presence of our atmosphere, and that oxide layer melts at around 3,600 degrees. Aluminum melts at 1,200 degrees. So if you take a pure piece of aluminum out here and you grind across it or you brush it with a stainless steel wire brush, before the brush gets to the other side, you've scratched that oxide layer off with the wire brush. It's already oxidizing behind you. But why do we like that property? Well, the reason is aluminum's oxide layer is clear, hard, and it's impermeable. So that oxide layer protects the aluminum from further oxidation. Who in here, be honest, because I'm going to tell you I've done it more than once, just twice, just to watch it, has ever taken a torch, typically an oxy-fuel torch, and melted aluminum just to see what the hell would happen? Oh, come on. Oh, there we go. There were some liars in the back for a minute. When you did that, did you notice that there was like a crust on top of the aluminum? It looked like a pie crust floating on the top of the puddle. Did you notice that when you melted it? That pie crust, the thing that's kind of floating on the top, is the aluminum oxide. At 1,200 degrees, roughly, depending on what you're welding, at 1,200 degrees, that aluminum melted. Okay? You didn't get to 3,600 degrees to melt the aluminum oxide. Do you know why? Because at 3,600 degrees, the aluminum would have already started to boil, and it would start popping. Pop, pop. And you can't get it hot enough to get it off. So how do we get it off? Well, we can manually clean it off. If it's something that's heavily oxidized, like a marine application, right? Marine application, got a lot of buildup. We can mechanically remove it manually. Stainless steel wire brush, wheels that are approved for use on aluminum. What's that? So you can use solvents, acetone, certain solvents. Acetone is my favorite. Acetone doesn't leave a residue behind. It flashes off really fast. Put it on a rag, wipe it to get the oils off. I just want to give this little point of note. If you put acetone on a rag and you lay it on your workbench, do you know what they call that? A wick. I might be speaking from experience. Stan had a question from the internet.
Can this be converted to use a wire feeder?
No. Wire feeder is MIG. Wire feeder is constant voltage. TIG is constant current. This is a TIG stick only. And was there another question back there where we were? Somebody, okay. We got to get that oxide layer off the aluminum. How we're going to do that is with the electricity. The AC sine wave is going to remove that oxide layer. There is a phenomenon that happens. For those of you who have your hand out, go to the picture of the sinusoidal wave. The one that looks like this right here. If you look at this sine wave, the way you read it, for those that don't know, an oscilloscope is like a television for an engineer. That's how we take and make something we can't see with our eyes that doesn't exist. We can graph it, and the engineer can measure it. He can take readings on it, see how it behaves when they do things electrically. So this electrical wave here is a way that an engineer is going to measure this sine wave. When the sine wave is up here, the electrode is positive. When the sine wave is down here, the electrode is negative. And in between, it's transitioning between the two. Does that make sense to everyone? Okay. The Linde Corporation, when they figured this out back pre-World War II, what they figured out was that the sine wave, as it starts to go to positive, will blast the oxide layer off the aluminum. Now why, if we're blasting it all off electrically, why does it not oxidize back? He's correct. He said the shielding gas. We are keeping the oxygen pushed away from it so there's no available oxygen to form an oxide. So as that thing comes, as that electrons come up, think of it like a submarine coming out of the ocean, right? As it comes up, they will blast the oxide off. You can see it with the naked eye. If you got under a welding hood here, I can weld some aluminum, I can show you it popping the oxide layer off. It'll all come off there. Now we don't have an oxide layer, so now we can get it to that, say 1200 degrees to make an aluminum weld, right? And then we want it to oxidize back when we're done welding. Why? Protection. It's like having your own can of Krylon coming right behind you, right? Any questions on that part so far? All right, back to the science part of it. Remember I told you when we were DC electrode positive, we never did that because we didn't want that tungsten to be positive because we had so much heat in the electrode, right? If everybody following that? Well, right here, guess what that tungsten is? It's positive. And when it comes down here, it's negative. That's changing back and forth. Can everybody see that 50% of the time it's positive and 50% of the time it's negative? What's 50% of 10,000? 5,000 degrees. So how hot does the tungsten get? 5,000 degrees, right? So the tungsten melts at 6,280 degrees. Can the tungsten handle that? Sure can it? That's how we can get away with it being positive part of the time. Any further questions on that? All right. We call this the cleaning part. We call this the penetration part. So we're cleaning, penetrating, cleaning, penetrating. We're getting the weld down into the root where we're welding. Now we're cleaning again, back and forth, back and forth, back and forth. Provided we've already cleaned that aluminum up manually, got most of the stuff off it, this machine will take all the rest of the oxides off for us, make a beautiful weld. Who's heard of a square wave machine? Somebody asked that on the internet a little while ago. Who's heard of a square wave machine? Anybody want to take a gander at what that is, what that does?
You have the hand covering the square wave sign.
Oh.
Rapid change from positive to negative on the sine wave.
That's not incorrect. He said a rapid change from positive to negative on the sine wave. That's not incorrect. That is Correct. But in a simpler terms, we take that curvy wave and we make it square. Now, why would we want to do that? Why is that?
Instantly go from the high current to negative, not that round transition.
So he said instantly switch from positive to negative. That's true, but let's break it down in a little bit simpler terms. Back at this sine wave here, there's a certain young man that's sitting over here in the corner that might be my offspring. And this is very much like him on a Saturday morning. We refer to this as a lazy sine wave. This is actually really called a lazy sine wave. The reason they call it a lazy sine wave, it's you're only at peak output a brief period of time. Can you see that? You're only brief period of time your peak, brief period of time your peak. The rest of the time you're spent transitioning, so you're not at peak output. Does that make sense? When we're in a square wave, we go straight from being output to output. The switch is instant. This wave looks like a square. If you go in your handouts and you look at slide number, I think it's 15. It is. Slide 15. These are different types of square waves. Okay, everybody there? Now, I don't agree with this artist's rendition because I've actually looked at it on an oscilloscope before. It doesn't have that little hoop at the top. I think they did that so you could see that used to be a curved wave. Whoever did this artist rendition, it actually is square across the top when you look at it on an oscilloscope. Okay? But what that does is allow us to be at peak output for a long period of time. Everybody see that? Now, I told you that when we were positive was when we did the cleaning, right? What if we could manipulate the sine wave to be more positive? What would that do for us? More cleaning, right? If it's a super, there's always that part that you're welding that no matter how much you try to get the wire brush in there, the wire brush just won't fit. It doesn't matter how many little special things you buy at the flea market that go in the drill to try to get up, and you can't get it. You just can't get it in there to clean it. Everybody knows what I'm talking about, right? So you could potentially take the machine and turn it more positive and get more cleaning. Everybody following me? Right? That's why he does that, but we'll get into that in a minute. What about the inverse? What about if we spent more time in the negative? What does that do for us? Say that out loud louder. More penetration. More penetration is correct. You're actually doing more welding. Everybody following that? So, if we can clean it manually, we can take most of the oxides off most stuff in our shop, we can spend a lot of more time in the negative side, meaning this little machine can now do so much more work for us. We call this balance control. Balance control is spoken in reference to negative. So if I tell you, when we're over there welding, what does your machine say? And I say it's 75% unbalanced. That means I'm 75% negative. Make sense? I only need a little bit of cleaning because most of these coupons are straight out of the aluminum mill or the steel mill. Well, aluminum mill if we're using AC. They're pretty clean. We've already wiped them down, got them prepped for weld. Don't need a lot of cleaning, just a little bit to get that oxide layer off. But I can set the machine now to do a lot more work without the machine having to put out a lot more power out of the wall, suck a lot more power out of the wall. Everybody following? Any questions on that?
So you're saying that 200-inch machines with square wave can weld thicker material?
Much thicker material.
Define much. 20%?
Well, it's relative to what you're comparing it to, but I've done all day long 1/4-inch plate with this. But now, I'm not in Alaska where it's cold all the time either. I mean, my ambient temperature is, this time of year is 95 degrees ambient. So like I said, it's all relative, and that's just trying to be fair to everybody. But these little machines, I don't know, 15 years ago, they don't do what they do now. because we've learned to manipulate that sine wave and get it so much more efficient. All right, high freak. High frequency. I'm going to talk about it and then tell you why we don't use it anymore. We don't use it anymore. We have to, and we still have to do this, we have to take and start the arc. Now, most people don't know this, inert gases do not conduct electricity. You cannot pass electrons. It does not like to pass electrons through it. It is basically an insulator. So what we have to do is ionize that gas cloud. Once we ionize it or electrically excite it, it becomes a pretty good conductor of electricity. Okay? Now, to prove the point, think about who in here is old enough to remember fluorescent light tubes that had mechanical starters. Raise your hands high so nobody thinks I'm crazy that's young. Okay. Those of you that are young, you'll never see them again in your life unless you go in your grandpa's barn, because he might still have some hanging in there. Fluorescent light tubes, for those who don't understand, used to have a mechanical starter in them. There's a little thing that looked like a blinker for a car, and it hung in the side typically. When you flipped the switch on, what happened was that little starter got an electrical impulse, and it shot a high voltage charge through the gas tube, which made it blink very brightly for a second. Blink, 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 blink. The point of that was to excite the gas inside the tube to ionize the gas to allow the electrons to flow through the gas. So the transformer would take over. Now the problem with those things, and everybody, whenever I say mechanical starters, anyone who knows them starts laughing, right? Because they were problematic at best. And here was the problem. The fluorescent lights would never turn on, okay, 50% of the time. And you would walk into the barn at night, flip the switch on, to see what's in the barn or in the shop, whatever, and the lights would flash 3 times really bright like a strobe. Now you're completely blind in the dark, can't see anything, and you have no light. The mechanical starters were problematic. You had to shake them, flick them, wiggle them to get them to work. Once the tubes came on, they worked great. The purpose of those was to excite that gas. We have to do that same thing underneath this tungsten in this torch. We have to excite this gas. Nowadays, we do it electronically with semiconductors. It's fail-safe. Every time you flick, fluorescent light comes on. I mean, those are a dying breed anyway. Everything's going to LED now. But the electronics take over. These machines now take over for electronically for us for the high frequency. But we have to create a high frequency arc in the very beginning when we start this up to excite that gas cloud to allow the electrons to be able to pass through that gas cloud. So they're jumping a gap. We used to do it with high frequency. The FCC has asked all the welding companies, said, hey, this is a huge radio transmitter coupled to 200 amps. It's really bad for TV for all your neighbors. Nobody listens to radio within 3 city blocks. You know, can we figure out a better way kind of thing? So essentially what happened is we now use what's called capacitance discharge. Capacitance discharge, you step on the pedal, it initiates automatically. It goes snap, snap, snap. You'll hear it, you can hear it. It'll hear it make a snap. It's just like a CDI ignition in a car or a internal combustion engine. It sends an arc across just like a spark plug, excites the gas cloud. Once the current is now flowing through that gas cloud, the electricity keeps it ionized, it keeps it excited. So we don't need it, we only need it on startup. Okay, these machines now do everything electronically. There is nothing for you to do. Just step on the pedal to start it. It'll start it automatically. Okay? Questions on high frequency?
Say hello to the people on Instagram. I got Instagram going here and you keep going there.
Hi everybody on Instagram.
We're getting quite a following over there. You've been on for about 20 minutes there.
Hey, I appreciate everybody on Instagram. Hope you guys are learning something. That's what we're here for. And what's that? You're not on, yeah, I'm not on TikTok. Oh, am I over here? And what about here? Here? Appreciate you guys joining in. Before Stan interrupted my train of thought, tungstens. Let's talk about tungstens. Now, some of the handouts, understand these handouts are from several different printings. Talk about the color code. They have the color code chart in them. The color code chart has changed multiple times. And I'm going to explain what that means. But for the sake of this discussion, just use the color codes as an example to guide you on what I'm talking about. Tungstens all look the same. You do not know that these are two separate tungstens, but they are. They're completely different. This is a chartreuse. This is a gray. This one's a purple, and this is another large gray. All right. What does that mean? The only way to qualify these as what they are is to put a color code on them. Okay? We're going to have to prepare these tungstens. We're going to grind the tungstens to get them ready to use. Guess which end we don't grind? Because once you grind the chartreuse off this one, you don't know any different from the purple, the gray, the yellow, the blue. There's many different colors. There are color charts to advise you on what they are. The color charts keep changing because they're evolving these tungstens pretty rapidly now. Some of this stuff is pretty amazing what it does. In the old days, was there anybody here that was taught to ball a tungsten? Besides you, Stan, you're old as dirt. Okay. Everybody out there in the internet world, if you were taught to ball a tungsten and you feel very comfortable and want to continue doing that very long and laborious process of balling your tungsten, there's nothing wrong with welding that way, but I'm going to show you a much better way to do it. You know what I mean? Like we flew across the ocean in a prop-driven plane, but now we fly in jets, right? People don't want to get rid of what they know, and I get it. There's nothing wrong with welding with a ball of tungsten. I'm not going to teach it to you. If you know what it is, and that's what you want to do, keep doing it. There's a much better way. We need to prepare these tungstens. The way we do it is by grinding them. We're going to grind them on a grinder. All of them, regardless of what variety they are, get treated the same. There's a lot of different grinders out there on the market. All of them work good. I'm not telling you need to go buy one. I don't have one. I wish I did. I just use the old bench grinder. Does anybody not know what a bench grinder is? I was here at one class and somebody did not know what a bench grinder is. I just want to make sure the nomenclature I'm using, you know what that is. So that is an electric motor on a pedestal or sitting on your bench with a grinding wheel that turns this direction. Everybody got that? We're going to grind these tungstens in a very particular manner. And if we grind them incorrectly, you'll say that I taught you bad stuff because you won't be able to weld. This is really important. The grinding wheel turns in this direction. Can everybody see that? Roundy, roundy, roundy. We're going to grind the tungsten in this manner. Okay? Do not go to the edge of the grinding wheel and grind it. My pop is 86 years old. If I ask him today, I said, Dad, can you go put a point on this? Guarantee you, without even blinking, my dad would go right to the side of that grinding wheel and put a point on it. If you do that, you will not be able to weld with the tungsten. Now, it doesn't ruin the tungsten, but it temporarily impedes the tungsten from being able to do what it's supposed to do. When you grind this way on the grinding wheel, you put scratch marks in the tungsten that go this way. Electrons flow on the outside of metal. They like to come off the outside. As the electrons come down, they will follow those scratch marks right to the point, and they will jump off the point. If you go to the side of the wheel, there's circumferential scratch marks. They go like this. The electrons will go to the very first scratch mark, and they will jump sideways. And they make a big umbrella of heat, like a rosebud. You can't weld with it. It's really simple. You just got to grind it this way. Now, I always get this question. I don't feel comfortable grinding this way because I'm afraid that the point is going to stick in the grinding wheel and it's going to shoot off and hit me in the belly and poke a hole in my belly. Can I grind it this way? Yes. The answer is yes. As long as the scratch marks go this way. That makes sense? Now, for those of you that follow that, I also know since you're a safety Nazi, that you have all of the guards on your grinder at home that it came with, right? The big guard and the little fiber or little Lexan thing that shakes, all of it jiggles loose. I know you guys all have it. You've never taken that off, right? So, riddle me this, gentlemen. If you're grinding your tungsten this way, and it gets stuck in the wheel and pokes you in the belly, or if you're grinding it this way, since you all have your guards on your grinder, and it gets around the grinder, goes around the guard, and comes out, where is it going, gentlemen? If I'm taking one for the team, I know where I don't want to take it. So, all joking aside, it doesn't matter as long as the scratch marks go this way. Yes, sir, question?
Now, I thought in the past you said that you had a virgin grinding wheel. You ground steel, aluminum, brass, copper.
You're putting the cart before the horse again, man. You're thinking ahead of the class. Hey, you're all over it, man. I appreciate the fact that you actually listened to me. It's the first time in my family that may have ever happened. He asked me about the grinding wheel. I was getting to that, but he is correct. It needs to be a virgin grinding wheel. You can use an aluminum oxide grinding wheel. Isn't it weird we keep talking about aluminum oxide? Notice, remember I said it's clear, hardened, and permeable? Aluminum oxide is second to diamond in hardness. That's why we make grinding wheels out of it. Super, super hard stuff. You can use an aluminum oxide grinding wheel to grind this. However, don't use that to do anything else with. Have a dedicated grinding wheel. The reason is, if you grind aluminum, because I know nobody has ever put aluminum in their aluminum oxide grinding wheel at home, right? Trying to smooth the corner out or something, that aluminum will impregnate on here and it'll jump across and mess up your weld. So aluminum oxide only wheel. You can use the green silica carbide ones. You can use the diamond wheels. The diamond wheels are the best, but you do not have to go buy a $120 wheel to grind your tungsten. You can go to Useless Salvage and buy one of theirs, okay? $6 wheel, put it on the grinder, take it off when you're not doing tungsten. Okay? Any questions? Anyone? Bueller? Anyone even here old enough to know that?
Question?
Are you done talking about tungsten?
I was going to talk about the colors and sizes.
Okay.
So, you have a question. Go ahead.
Wanted a question, I've got a question for you.
I'll answer a question to the best of my ability.
Are there any jigs or anything that is, or I guess the first question is there a proper angle, and are there any jigs to help you achieve that?
So his question is there a proper angle? And is there a jig available to help that? So the advice we give people is 1/3 the rod diameter in pitch, which is really hard for me to figure that math-wise out in my head anyway. So here's what I'm going to tell you. As you grind tungstens and you practice welding with them, you will begin to find the angle that you like the best. Some people like a very blunt, a more blunt angle, and some people like a more needle point angle. The one thing that's important when you get and you're grinding that needle point angle is that tungsten gets super thin on the end. Take that grinding wheel and just lightly bump and just knock that point off it. The reason being is all of that current will come through that point, it'll make a little tungsten ball, and it'll jump across your weld. So blunt that end off there. More to your question, there are guides, there are all kinds of guides out there, yes. Even those little Dremel, the little Dremel style, look like a little Dremel that you can sharpen your tungsten, they're super slick. They hold it in like a little arbor and keep the right angle on it. But as you develop in your welding and get better at it, you'll find an angle that you actually like a little bit better. It's not super crazy, but you're like, well, I kind of like that angle. It came out a little bit better or worse, vice versa, whatever. Stan has a question from the internet.
Any health risks while grinding?
Are there health risks while grinding? Well, being that I'm in the state of California, and the state of California has determined that bottled water, fresh air, and sunshine can lead to cancer in laboratory rats. Yes, the answer is yes. This is a heavy metal. Okay, tungsten is a heavy metal. So the dust from it should not be breathed in. Now that being said, there's guys that have been grinding tungstens for years with no health risk. Well ventilated area, if you're one of those guys that are super safe, nothing wrong with that. You can do the shop vac to the, you know where the grinder drops out, there's the guys that make like a little shop vac attachment that collect all the dust off of them. Typically speaking, as a home shopper, not a guy who's doing it for a living, but a home shopper, we don't grind this enough. Now, red tungsten. Notice we talked about the colors a minute ago? Red tungsten. Red tungsten is not available in this state anymore because California says you can't sell it because it's got 2% thorium in it. It is not 2% thorium. That is a misnomer. It's 2% thorium oxide. They're not exactly the same thing. However, they're not to be sold in California anymore. So that's why we have the purples, the blues, the chartreuse, all the other ones they've come out with that alternately replace red. Red Some people feel that it has a radioactive element in it and that it's bad to breathe. I cannot tell you that it is not. I cannot tell you that it is. I know lots of people that are, of course.
Now, with the radioactive thorium, is that
It's not thorium, it's thorium oxide. Thorium glows at night without a light on. Thorium oxide is a derivative, it is thorium, but it's in a different form.
the difference in what we're building from thorium oxide versus
Okay, so looking back on, like if you're looking at a timeline of history, we had green, we had red, I think we had yellow, we had a couple of choices, and that was it. You had to make whatever you had work. Red has always been, we've used it for years and years and years. It's a very good product, it works well, but because of the fear of the thorium oxide, they've developed others that actually start to work even better than the red now. People ask me, what do I buy? Here's my spiel on tungstens. Everybody's going to go, when they start off, is going to go want to get all the stuff they need. When I started off, I just got my first real job. I went into weld supply. I said, I want to learn to TIG weld. I want you to give me everything that I need. And that guy behind the counter went, yes. To this day, just because I cannot get rid of it, I still have unopened boxes, 30-something years later, of stuff that guy sold me. So I try to let home gamers, guys at home, not spend a ton of money until you figure out what works for you. You know, because everybody likes their seat in their car in a different position. Some people like it lean back. Some people like it sitting straight up. Some people, like my wife, like it right in front of the steering wheel, right? Everybody has their thing that's comfortable for them. So where's a good place to start? I'm going to give you a couple colors that I like. My suggestion is if you're going to do this at home, go buy one or two of those colors and try them. The tungsten is not a one-shot deal. You keep grinding it and reusing it. When it's time to buy another one, maybe try a different color. Don't go buy, like I did, 5 boxes of all the different colors that I'm never, ever, ever going to use. Never. I'll never use them. Because they sold me a lot of stuff. Now, tungsten come in different diameters. Why do they come in different diameters? Anybody know? Heat is correct. Stan? Was that an answer or?
No, properly heated tungsten conducts electricity properly. A cooled tungsten does not conduct electricity properly.
So he is correct. It is heat. So we're not going to put 250 amps through a 1/8 tungsten. I mean a 1/16 tungsten. We're gonna use a 332 tungsten for that. Now, what sizes do you need to start in your shop? I'm going to give you 2 sizes. Buy 1 or 2 of each, and that's it. That's all you need. A 1/16 and a 332. If you get into some super thin aviation stuff, maybe go to a 40,000 tungsten. But for the most part, you don't need to buy boxes and boxes and boxes of this stuff. On Stan's point, what Stan said was, tungsten likes to emit electrons at a very specific temperature. So, if I take a big tungsten and I try to weld with 12 amps, the tungsten doesn't get hot enough to become a really good emitter of electrons. So those of you that already TIG weld, you probably notice sometime when you start, you'll notice the arc will jump around here a little bit, swirl around. The reason is the tungsten hasn't come up to temperature to become a really good emitter of electrons. If you go to a smaller tungsten and you're welding at a much lower amperage, that tungsten will warm up much quicker and sustain that temperature where it emits a good electrons. Gives you much more control, in essence, of what you're doing. And a little tiny 1/16, you're not going to put 250 amps through that because eventually this is going to overheat and give up the ghost. It won't hold that point as well for you either. Did I hit it all on that? You got any more internet questions? No? You were asking, sir, about the, there's a picture that's in the handout on grinding the tungsten. Here's a picture of what balling a tungsten looks like if you learn to ball it. And that's what you want to do, keep doing it. I'll never ball another tungsten if I can help it again in my life. But that doesn't mean it's wrong.
John Marcus says that Amazon still has thoriated, and they will ship to California.
So,
We don't know how long that's going to last.
yeah. As soon as this broadcast hits out that they're Amazon selling 2% red thoriated, somebody says it's available right now online if you want the red. I've welded with red for years. It works well, but I can tell you that the chartreuse, the purple, the blue, the gray, all of those work great. Pick one and start off with that. If you want to try something different, you know, everybody has their thing they're like. I mean, I'm going to light the internet up in a second, and everyone's going to say bad things about me, but here we go. It's really, really this simple. You guys see this? Ford, Chevrolet, Dodge. Ford guys walk, Chevy guys go fast, and you won't go far in a Mopar, okay? Everybody has the thing that they like. You know, I mean, if it's a Ford, at least they circled the problem, right? Did you guys know that the 12 apostles were all Ford guys? They walked everywhere. I have a Dodge and a Nissan, so I'm bipartisan. You know, whatever. Now I do have I forgot about the old Chevy truck. Oh. I've already written that off. My son's going to drive it. It won't last long. I was talking about the truck, not your driving. Anyway, it's really.
Is that kid driving? No.
He does on the farm.
I'm not. Okay.
So it's really a preference thing. That's really what it comes down to, folks. And everybody has their thing that they like. So, I mean, if you're a Ford guy and you like to walk, you know, buy a blue tungsten, whatever. No, I'm kidding. It's a joke. They all work really well. Just pick one, try it, and find out what you like. Any other questions? Yes, sir.
Yeah, on the back cap, I'd loaned my TIG welder to a friend of mine who broke his back cap off, and he says take JB Weld and weld.
No. The back cap costs a couple of dollars. They're not expensive at all. Go on Amazon and have it to your door by tomorrow. If you get a crack, he said put that on there with JB Welding. You get a crack in there and it starts sucking air in there, messing your weld up, it's not worth the money to me. I mean, whatever, it'll seal it.
And doesn't it get kind of hot back there?
It does.
And I don't think JB Weld takes high temperature.
I don't know what JB Welds. I stay away from JB Weld. Question in the back, yes sir.
Is there a preferred manufacturer regardless of color tungsten?
No, I don't have one. I think Radnor is one of them, the companies out there that make some. There's a lot of different companies making them. A lot of them coming over from the big pond, coming over to us because they're heavy metal and, you know, restrictions and all that. Any other questions, comments, concerns? Anybody? We're going to go till we stop because the feed's going live right now. So we'll talk real quickly about aluminum and filler metal, and then we'll kind of wrap it up if we don't have any other questions. So aluminum has about 7,000 places on the alloy chart. There's about 7,000 slots on the aluminum alloy chart. There is literally no way that you can remember all of those alloys. 2024, 5052, 6061, 6062, all of them. You don't know. When you go to weld aluminum, aluminum is one of those things. There's a couple of filler metals that work most of the time, but if it's anything important, listen to what I'm saying. If it's anything important, like an airplane wing, 100% of the time you never guess. If it's a garbage can toter hauling your garbage cans out to the curb, and you want to practice with it and the wheel falls off, the worst it is you're going to have to pick up garbage out of your yard, right? When you're welding aluminum, you absolutely have to figure out the base alloy and the correct filler out. Now, here's the trick. Everybody's probably heard of this thing called Google, right? Go to Google, type in aluminum alloy chart, and typically the first one that's about 7,000 of them pop up. It's typically Alcoa, because Alcoa is one of the largest manufacturers of aluminum in the world. Alcoa aluminum, just click their alloy chart, they're all the same. You know I'm welding 5052 aluminum. It will tell you first choice, second choice, third choice for filler in order of preference. Like what's going to be the easiest, best weld, second best, or not acceptable, or so on and so forth for every one of the alloys. Okay? If you want to join one to the other, and this one has a filler metal, and this one has a different filler metal, when you join those together, that is not going to give you a good weld because those two alloys don't go together. Any questions? Are you guys getting hungry? Is that what's going on? Listen, man.
Tremendous information.
I just got outranked by a hamburger. Wow. All right, folks. Well, if there's no other questions, we'll wrap it up here. A couple little closing remarks here. If you haven't subscribed to my channel, I'd appreciate a sub. Reach out there. It's Do Right Fabrication. I'm on Facebook under Do Right Fabrication and on Instagram under Do Right Builder. And I also want to thank, again, my sponsors, Lincoln Electric, and mention the coupon code. This is good, I think, till the beginning of August, sometime around there. These coupon codes, it's $400 off these machines. It is 20% off all of their apparel, helmets, safety gear, all that stuff, 10% off any additional equipment. So if you want to buy a MIG machine, you want to buy a plasma cutter, it's an additional 10% off that. The bash codes are here. There's 3 different bash codes there. I would appreciate you using that code because that shows that you are watching. Anybody have any questions about the TIG 200? Who's got a question? Go ahead.
You said something about some classes tomorrow?
There's hands-on portion will be tomorrow. So tomorrow, it's first come, first serve. Until I get tired and cranky. We're probably going to start around 9:30, 10 o'clock. We don't have a specific start time just yet, just because there's a huge influx of people and there's a lot going on. But we'll just give everybody about like 10 minutes of hands-on time to get under the hood, try to weld. We have some mild steel, we have some aluminum. Everybody can look. The neat thing is that you don't actually, the weld booth we have, you can see through it, so you can stand around and actually watch other people weld. It isn't it's one-on-one, but you can learn from the other folks here that are welding too. Any other questions about anything going on? Everybody? Yes, sir.
One last one. I heard that we're giving away one of these.
There is a raffle. You have to be here tomorrow to win it. There is a raffle. We are giving away a TIG 200. You can put your raffle tickets in the bucket for the TIG 200. These were brand new. I just took them out of the box. Any other questions? The raffle is gear pack, cart, TIG welder, everything you need to get started. Minus the whatever you need to fix or make and a bottle of gas. It's a complete start setup. That's compliments of our friends at Lincoln Electric. They donated that.
Welding table, does it need to be grounded?
The welding table does not necessarily need to be grounded. Your part needs to be grounded. But if your part is grounded, you want your table to be grounded. Does that make sense? In other words, can you weld on a wooden table? Yes, you can, provided you don't put heat into your wooden table and destroy your wooden table. But if you ground your table, you ground your part on your metal table, you want all of it to be the same potential. So the part and the table to be the same potential. In other words, you don't want the arc to jump to the table and not the part. That makes sense? Any other questions? Everybody got it? Good? I appreciate everybody coming. I appreciate the subscriptions and the following us. It helps us be here. I, again, appreciate Lincoln Electric. You guys go out and give them a big thank you, everybody, for being here this year, especially in such hard times in our country, getting product moved around. It's tough on everybody, big and small. Is there any questions, Stan, before I sign off?
No, I think we're good to close. Rico says thank you to Stan, thank you to Jim. Bye, good information here. Thank you, Jim.
Yay! Thanks, everybody. All right, I'm just going to walk off camera now.